Welcome back for our last day. We're starting today with Patricia and also Sergio. They're going to share this hour today talking again about vertex composability.
Thank you for the introduction. Thanks all for coming back. I know it's been a busy 2 weeks and it's exciting to start off the final day. So let's recall roughly what we're doing here. Our goal is to understand a homogeneous ideal I of the polynomial ring k adjoin x1 to xn. Specifically thinking about this as the defining ideal of a projective variety, so something embedded in P n minus 1. So we want to understand invariants like the dimension and the degree. And these are both invariants that are preserved under Gröbner degeneration. So we will do this via Gröbner degeneration. And in the classical case, this is we replace I by some initial ideal, some monomial ideal that we very much hope is square free. Because if it's square free, then the extremal Betti numbers agree by Kuhnke-Barbaro. And so in particular, we can say that I is Cohen-Macaulay if and only if its initial ideal is Cohen-Macaulay, and the Casanova-Mumford regularity agrees. So in the very good case, we go straight to a monomial ideal, and then we use those tools that Sarah taught us about in week 1 for studying square-free monomial ideals combinatorially and topologically. One challenge that can arise is maybe our ideal has no square-free initial ideals, and there's an example of this on the exercise. And so by just degenerating a little bit here and a little bit there, we can stay radical in sort of enough pieces that we can still use these combinatorial strategies and then just piece back up together the information. So we can avoid some failures of reducedness by degenerating piece by piece. Something we're going to think about today is a different way where degenerating a little bit at a time is helpful. And that's in the case where I is defined using some combinatorial structure. So what I have in mind are various kinds of determinantal ideals. So these, very classically are just fix a matrix, fix a size of minor, take all of those minors, generate your ideal. But when we say, determinantal ideals, maybe these days we also include things like matrix Schubert varieties, or ideals, I guess, Schubert determinantal ideals. So there are a lot of things that are defined by determinants, where I get some combinatorial structure. If we go all the way to the initial ideal, we lose a lot of that structure, and it's hard for us to tell what's going on. But if we degenerate piece by piece, then we're getting a little bit closer to this union of coordinate hyperspaces. Union of coordinate subspaces. But also, we preserve a lot of the combinatorial information that defined our ideal. And so we can track things more easily. And we're going to do just the classical determinantal case to model how a geometric vertex decomposition argument looks. And then Sergio will talk a lot about graphs. Graphs are another case where, the graph is obviously a big combinatorial piece of information. It defines our ideal. If we go all the way to the initial ideal immediately, we lose the whole graph. But maybe we could just lose some of the graph in a small amount of degeneration. Okay, so proposition. This is a very well-known result by many different kinds of arguments by now. And we're just going to use this for the purpose of modeling a geometric vertex decomposition argument. So proposition, I'm going to set my notation in the proposition. This is bad form, don't do it. But you know, I already wrote prop. Let Mn denote the ideal Z11 up to Z1n, Z21 up to Z2n, Zij, all distinct variables. Let I2, it's the only one that's going to come up, of a matrix, be the ideal generated by the size 2 minors of the matrix. Then I2 Mn is geometrically vertex decomposable. Of height n minus 1. And I'm putting in the height because this is going to be helpful for us through an inductive argument. So before we actually prove this, we'll say fact the given generators of I2 and N form a Gröbner basis. They're actually a universal Gröbner basis, but relevantly for us, under the term order that is Lex with respect to, I'm going to name this term order that. Z2n is largest, then Z2n minus 1, and it actually doesn't matter what happens after the first step really, but we'll end with Z11. So we have this Gröbner basis. Once we have a Gröbner basis, we're in position to do geometric vertex decomposition. And I guess on this board, I'll also recall our proposition from last time, which will be, well, no, I'll just put it on a different board. Sergio's using slides. I don't have to worry about being board greedy. So recall. This proposition from last time. If C and are homogeneous, it's homogeneous, that J equals FC plus N. If F is a non-zero divisor modulo N, and R mod N is Cohen-Macaulay, and the height of N equals the height of C minus 1, then height J equals height C, and R mod J, Cohen-Macaulay, just unmixed if we care about that. If and only if R mod C is. Okay, so let's practice our notation. First, I'm going to set y to, what should y be in our usual notation? Given this setup, anyone can just shout it out. Yeah, z2n. So, I'm sorry, z2n. So, we take y, just going to be the name we give our next largest variable. And it's going to be named I. Oops. What is the ideal C? How do we get that? This one, maybe I'll say some words and then I'll ask you to shout. So C says I take every generator that involves Z2n and I pick out the thing that's being multiplied by Z2n. So for example, if I have Z11, Z2n minus Z21, Z1n, this tells me that Z11 is a generator of C. Someone shout out another generator of C. Z12. Someone shout out another generator of C. Great. And do I include Z1n or not? No. So I get top row, the first n minus 1 of them. So at least we start there. Thanks. Okay. We also have to have all of the generators that do not involve Z2n at all. So for example, we have Z11, Z22 minus Z21, Z12. That is an element of C. Do I have to write it down? No, yeah, I see a lot of head shaking no's, and that's because once I have these two variables as generators, this whole minor is in there. So it's in my ideal, but I don't bother to write it down. These are the H's in our usual notation. Same for any minor that doesn't involve the last column. Every minor that does involve the last column involves a Z2n, so we already accounted for it. So that tells us that C is just identically this ideal generated by variables. Okay, so then N well, N is by definition the ideal generated by all of my Gröbner generators that just don't involve Z2n. So this is I to M n minus 1. So I'm just cutting off the last column. All right, so we're hoping we're hoping to make use of this. So let's just go through and check stuff. Is everyone in sight homogeneous? Yes. I guess we have to actually write down the equation now. Notice in yi, so in yi is the ideal where we're setting Z2n, we're giving it weight 1 and we're giving everybody else weight 0. And then for each generator, we're just taking the highest weight terms. So if I include Z2n, then my initial term is, for example, Z11 times Z2n. or Z12 times Z2n. And if I don't involve Z2n, then both of the terms win because they're both weight 0. So that's telling me that in yi, Sergio is very accommodating on notation, and one thing was asked of me, and that's that I write in it instead of in. And so far I've done that 0 times. Now I succeed. Okay, so in yi is y times cyi plus nyi. These are exactly the generators that we just described for nyi. And this is typical for a geometric vertex decomposition. This is a geometric vertex decomposition at Z2n, and we get this equation from it. So it's not specific to this case. All right. The monomial Z2n is homogeneous. We have this equation. So now J is playing the role of I. C and N are C and N. F is Z2n. Is Z2n a non-zero divisor modulo the ideal of minors that don't involve the last column? Let's take a look at a small example because I see some blankness. So Sergio gave us the 2 by 3 example. So this is going to be Z11, Z22 minus Z12, Z21. C is going to be Z11, Z12. Y is going to be Z23. Is Z23 a non-zero divisor modulo n? Yeah, because this variable is not involved in the generator of this ideal. It is not in the support of any of the terms. So this is an ideal in a smaller polynomial ring. All of its associated primes can be viewed in that polynomial ring. So this is not a zero divisor. Same thing over here in the larger case, where this ideal has generators that only involve the variables whose last index goes up to n minus 1. So this Z2n is not in any of the associated primes, because those all live in the smaller polynomial ring. So not a zero divisor. Okay, now I want R mod n to be Cohen-Macaulay. What's something that I can use to conclude that n is Cohen-Macaulay? Or what's something that we know about n by induction? We know its height by induction. Oh, and then maybe we would, if we have some resolution information, we could say that its height was the same as its projective dimension, and we could conclude Cohen-Macaulayness directly. That would be great. I'm going to skip. That is a good suggestion, which I will not take. Does anyone else have a suggestion? Well, let's forget about Cohen-Macaulayness for a second. We want to run a proof by induction. What's the other thing that we get to conclude by induction? GVD, yeah. So by induction, R mod n is GVD, so geometrically vertex decomposable. Recall, geometrically vertex decomposable plus homogeneous implies, just by context cues, what's probably going to go on the right side of this? Oh, wow. Yeah, let's do it. I bet you can guess this. Let's do it louder. What's the thing that we want to appear here? Everyone together? Cohen-Macaulay. And indeed, that's true. Yeah, so geometrically vertex decomposable implies Cohen-Macaulay. It's one of the reasons why it's worth studying, in my opinion. So by induction, we're getting that R mod n is Cohen-Macaulay. Also by induction, now I'm ready to take the suggestion. What was your name? I'm so sorry, I've forgotten. Chris. I'm ready to take Chris's suggestion. Let's record the height. So the height is one fewer than the number of columns. So n minus 2. Okay. Note, the height of C. C is generated by a bunch of variables here. So in the maximal minor case in the homework session, you'll want to use an inductive strategy to get the height. But here, if anything has height n minus 1, this ideal does. Since it's generated just by n minus 1 variables. And my height should be the longest chain of primes that I can get. So my chain of primes is just going to be 0 to this one, to these 2, and so on. Okay, so the height of C is 1 greater than the height of n. We have Cohen-Macaulayness. Now we get to conclude by star. Height of I is also equal to n minus 1 and R mod I is Cohen-Macaulay. So this is how a typical geometric vertex decomposition argument works. You have some class of ideals. You want to describe it broadly enough so that the things that you get by geometric vertex decomposition fall into your inductive case. You want to, as much as you can, use this to get unmixedness, because unmixedness is usually hard. Cohen-Macaulayness is strictly stronger, but sometimes easier to establish. We have more characterizations of it. So here, for example, we just said Cohen-Macaulay, and I didn't even bother to write therefore unmixed, since Cohen-Macaulay was our goal. So we use induction. We use this as well as we can to do the heavy lifting, and then we get control of Cohen-Macaulayness and of height immediately. Who wants to take a victory lap? A couple of you. I want to, and I seem to be holding the chalk. Oh, perhaps some of us are unfamiliar with the phrase victory lap. So if you're like running a race around a track and you win, then people are so excited that they run just a happy little jog to enjoy the victory. Now who's excited for a victory lap? Okay, so 1, I is unmixed. A couple ways to see this at this point, but Cohen-Macaulay implies unmixed is the best. 2. This is, so fact. R mod I is regular. for all P in spec I of type 1. So this is regular in codimension 1. It's pretty weak. This is an optional exercise if you've seen this type of thing before, but we're going to take this. So by special case of exercise 12, 3, R mod I is normal by 3, oopsie, by, I guess our main conclusion. So CM plus 2. Normal can be characterized as satisfies Sarah's condition S2 and also R1. Cohen-Macaulay implies S2. So in that sense, geometrically vertex decomposable is good progress towards normality if you can control the singular locus in a kind of mild way. Being singular in codimension 1, I mean, that's so singular. And determinantal varieties are our friends. 4, I is prime by exercise 10. So once you get geometrically vertex decomposable, it's more work to get these other things like normal and prime, but you've made good progress. So this is a tool that you can use to study these other core properties that we like seeing. Okay, are there questions on this? Any of this? Anything we've forgotten about geometric vertex decomposition? Now is a good time to ask. Okay, the very final thing that I want to say is also geometric vertex decomposition can be used to establish Gröbner bases. As in, should receive G, J, K, L, M, Migliore, Nagel, Gorla. So here it was sort of under the name liaison theory. We now know that these instances coincide. So I'm going to state a version of the implementation that sort of lets you not give isomorphisms of quotient modules and lets you implement pretty directly. So this implementation is from my paper with Jenna Radschott, but the idea is due to Migliore, Nagel, and Gorla. So prop if I y q1 plus r1 y qk plus rk h1 up to hl is homogeneous. Y does not divide any term of any qi, ri, hi, so linear in Y. Fix a term order less than. If GC Q1 up to QK, H1 up to HL. And GN, H1 up to HL are Gröbner bases. For the ideals they generate are going to be called C and N. If the initial term of each YQI plus RI is equal to the initial term of the part with a Y, if the heights are what you would want, so in this case we just actually need height I and height C strictly greater than height N, and N is unmixed, and this is kind of the weird part. The ideal of size 2 minors, Q1 up to QK, H1 up to R1 up to RK. Is contained in N. Then the given generators of I are a Gröbner basis. So this is just saying, if it looks like you should be able to do a geometric vertex decomposition, and this particular ideal happens to be contained in N, then you get to conclude that the thing that looks like a Gröbner basis is a Gröbner basis. So you can use this to show the thing that we assumed, to show this fact. So you can get this fact at the same time you're doing the induction on cone Macauliness and height and other things. So a strategy that Eliza and Juan and Uwe gave us was you go down inductively and you just get everything by induction all at the same time. You're getting the height, you're getting the cone Macauliness, you're getting the right Gröbner basis. And this is going through a Hilbert series argument. This you maybe want to think about as S pairs for the weight order that does a geometric vertex decomposition. Often in combinatorial settings, most of these assumptions are cheap, and this you need to know something about. Okay, I'll stop there and turn it over to Sergio.
So I'm just going to be talking about toric ideals of graphs and sort of using GVD to study properties about toric ideals of graphs. And I really like this family of graphs because life is really easy there because a lot of the stuff that we need to do GVDs is already established, and we can kind of just, go forth and start finding GVDs. So here's a nice picture from Alan Knudsen on vertex decomposabilities. You've got the star deletion glued along the link. So this we already know. We get that homogeneous in GVD implies Cohn-Macaulay and this Clichy property. So this nice property from the liaison theory side. And you know the picture already from Patricia's talk. So toric ideals of graphs, what are they? So let's fix some finite simple graph G, vertex set V and E. And then you define these two polynomial rings on the edge set and the vertex set, so the variables in those sets. And then you have this K-algebra homomorphism where you map the edge variable to the product of the two vertices. Okay, and then you ask for the kernel of this homomorphism, and that's going to be the toric ideal of a graph. So you can study from that perspective, but there's a nice description of its generators, which is just going to be in terms of the closed even walks of the graph. Okay, so even uses an even number of edges, closed starts and ends at the same vertex. So just walking along the graph. And there's sort of like this minimal description in terms of primitive closed even walks, right? Because technically you can just kind of go around, the graph as many times as you want. So first of all, how do we get binomials to in our ideal? So let's say that we have, does this point? Oh, it does, okay. So let's say like we have like the GEFA, so like this 4 cycle over here. So I wrote down those edges, and you kind of just throw them into like in an alternating way to the each part of the binomial. Okay, so it's going to be FG minus AE. You can also do like G, GEFA, and then G again, DCB. And it's going to give you this binomial here. But then you'll notice that this FG term divides the CFG squared, and then the AE divides the ABDE. So we say that this larger polynomial is not primitive, right? And the first one ends up being primitive. So particularly the even cycles are going to be primitive, and then you get some other patterns more complicated for other graphs. It turns out that the primitive closed even walks define a universal Gröbner basis, right? So this means that it's a Gröbner basis with respect to every single monomial order on your ring, which is good for GVDs because you need to work with a Gröbner basis. And if you didn't have a universal Gröbner basis, you have to keep changing things as you're trying to discover what's the right GVD. So with torqueted as graphs, you kind of just have this set computed, at least for small examples, and you just start working on the GVD process. The other thing with torqueted as graphs is you also, if they possess a square feature generation, you don't just get this radical property, you also get normality and Cohen-Macaulay, right? And this is due to results by Hochster and Sturmfels. And in terms of like the induction process, torqueted as graphs are nice on the n ideal side. So here you just see that the n ideal is just going to be this toric ideal of a graph deletion. So you did that exercise where it's like the n ideal was just these HIs, the stuff that doesn't involve the variable y. So in this setting, it's going to be like the set of primitive closed even walks that don't involve variable y, which are exactly the walks in the graph deletion. So it's fairly easy to see that result there. Okay, so let's just see an example of kind of how you do a GVD for specific graphs. So let's work with like K5. So Villarreal has these nice generators, these nice quadratic generators for Kn. And so I've listed them on the left-hand side. And the monomial order starts with x45. So I've highlighted that in green. And on the right-hand side, so the n ideal, we already know what that is. That's just the graph deletion. What happens with the C ideal? So with the C ideal, you're supposed to extract these coefficients here, right? So you got your x12, x13, and x23. So they're there. It's supposed to be pink, but it looks purple on the screen. I don't know what that looks like to you, but and then you have all those other generators that don't involve x45. Now what happens is you get like this coefficient part plus like this other part with binomials, right? And then you're going to get some cancellation going on. And in this case, the cancellation happens up here. And then you say, okay, well, what's left over afterwards? Because you have to start thinking about prime decompositions for these things if you want to continue the process. And you kind of notice, oh yeah, these are just the generators for like this bipartite graph on the purple vertices to the green vertices. So like, good. You notice a pattern and you say, okay, well, maybe it works like this all the time. And it does. So the idea is that you sort of get this, you get this n ideal, where so it's complete graph minus this vertex. So you're actually not inducting on just complete graphs, right? You have to do complete graphs minus a certain number of, sorry, I said vertex, I meant edge. So complete graph minus a certain number of edges. And then on the C ideal side, you kind of get this nice property where you get this ideal of indeterminates plus this toric ideal of a bipartite graph. And now we have a bunch of tools that we've come up with before this to kind of help with the situation. So the important thing I probably should have shown in the previous one is that what remains, so the generators that remain here don't involve obviously the x12, x13, and x23. So sort of defined on disjoint edge sets. So there's this result that we have in my paper with Jenna, Adam, and Mike, where if you have I plus j and I is defined with like one set of variables, j is defined with another set of variables, then I plus j in this ring is going to be GVD if and only if it's GVD in the smaller rings, right? Okay, great. So I could break this up into two pieces. And then you say, okay, well, this is already GVD by definition, right? That's one of the base cases. You have an ideal of indeterminates. So life's good. And then what about the other case, the bipartite case? So now we need another theorem from the same paper where bipartite graphs are GVD. Okay? And then continue by induction, and as Trisha said, do the victory lap. You have a GVD for complete graphs, which is great. I don't have time for questions, so I'll ask afterwards. Okay, so what if you wanted to kind of deal with, okay, so what's the goal for toric ideals of graphs? Well, you want to start classifying which ones are GVD. So what's kind of the next best thing is like, okay, maybe quadratic Gröbner basis, like if you have a quadratic degeneration. And those quadratic generations are going to be square free, actually, because of properties of toric ideals of graphs and primitive closed walks. So in the quadratic case, you know, in the exercises you showed that the Gröbner basis for I descends to a Gröbner basis for n and c, right? Each of the respective pieces. So you kind of have these quadratic Gröbner basis for n and c, and then you can show that, okay, well, c is going to be this ideal of indeterminates plus the n ideal plus this toric ideal of a graph. Your only worry now is going to be, like, what cancellation do I get, right? Because if I get cancellation where it's like I only get one monomial piece left over, like it only cancels one of the terms, but you get something else, then it starts getting messy. The good thing is that if the cancellation happens, it cancels out both terms. So it's like it either completely vanishes or it doesn't involve the variables at all. So you can kind of see now the parallels between the complete case, and then you can kind of get a GVD that way. Quadratic Gröbner bases are really nice. They're studied. So if you have quadratic Gröbner basis for a toric ideal of a graph, that implies that the edge ring is causal, and it also implies that IG is obviously quadratically generated, not necessarily by Gröbner bases. The implications are this way, and there's counterexamples for you can't go the other way. And what's nice is that there's this characterization by Hibi, Nishiyama, Osugi, and Shikama, which gives you sort of this side of the equation, so necessary conditions for, if and only if conditions for being quadratically generated, which gives you necessary conditions for having the quadratic Gröbner basis. So you can start to understand like which graphs kind of look like the quadratic Gröbner basis, you know, in that setting. Square-free degeneration would be the next step after that, and it's becoming a more complicated question, where we're starting to find examples where, yes, all the GVD cases that we've seen so far, up to like 12 edges or something like that, they have square-free degenerations, but there are square-free degenerations that don't give you the GVD structure, so it's not really clear how those two things are related. So I'll just leave it as a very open question right now, whether that's there's something there. Okay, so now I'm just going to kind of rapidly, we only have like 5 minutes, so just kind of go through like what's going on in the GVD setting for toric ideals of graphs. So we have these other versions of GVD. So Jenna and Trisha have this weekly GVD property where you kind of check like one side of the GVD tree, like the C ideals, and then the ends have to be sufficiently nice too. So Cohen-Macaulay, I think, and radical. And then there's this GVD allowing substitution. It was also inspired by Trisha and Jenna, where you can you can allow for some powers, okay, in certain settings, right? So instead of just the, you know, n plus y, you can have n plus y to the d, and then you can kind of decompose that way. So if you allow that, then you can also talk about weekly GVD allowing substitution. You get these implications. You still get the Glichi property. You still get the Cohen-Macaulay property. So all these things imply Cohen-Macaulay, and you have all these tools at your disposal for sort of, you know, attacking the graph problem. So then you can start asking, okay, well, which graphs are GVD of substitution but not GVD? Which ones are weekly GVD but not, you know, GVD, whatever? Like which one's in what category but not the other category? And do you see certain properties in those graphs to, you know, utilize for your proofs? So you start computing examples using the code that I mentioned that Mike and Adam have in Macaulay too. And so, for example, here's like just a sample of the graphs from GVD of substitution but not GVD. So the easy ones are kind of like these ones with the bridges, right? So those ones are like going to be GVD by substitution. When you talk about the primitive closed walk here, you have to kind of cross that bridge twice to complete the loop. So you get that square term, right? So, you know, these are fairly, you know, you can sort of guess those once you study GVD by substitution. But like, you know, once you don't have the bridges, it's not really clear like what the pattern should be, right? So, you know, if you can find something and you can prove it, then you would have classified some subgroup of graphs for GVD purposes. Okay, so all of these GVD properties imply the Cohen-Macaulay property, so maybe we can try to, you know, attack the which graphs are Cohen-Macaulay question. So that's a difficult question. I don't know if Selvi's here, but you can talk to Selvi afterwards about that's a difficult question. And here's an example where the graph is Cohen-Macaulay, but if you delete the vertex x5, then it's not Cohen-Macaulay. So you have this induced subgraph, which is not Cohen-Macaulay within the graph, which is Cohen-Macaulay. So we kind of looked at this example. So this is work with Mike. It's not GVD like in any of the senses that I had in the previous slide, okay? It also, incidentally, does not have any lexicographic square free degeneration. And you can show still, you have to kind of, you partially do the GVD process up until it doesn't work anymore, and then you have to kind of do the linkage manually. But you can show that this actually is Gleachy. There's like this conjecture from liaison theory where it's like every arithmetically Cohen-Macaulay projective variety is Gleachy. So we don't have any contradictions there with this example. Then you should start asking, okay, well, which graph operations preserve the GVD property? Because you need to start doing constructive stuff, right? You can't just, find low dimensional examples. You have to start constructing upwards or downwards, I guess. So one of the properties that kind of works nicely is something called star contractions, where if you have a vertex, so let's say we do a star contraction along V6. So you want to do an edge contraction along each of the edges incident to that vertex, right? So it's like E and F. Right here. So E and F in blue. So I highlighted those in blue in the generating set. So after you do the contraction, V1 and V5 will be identified, and you kind of get this multi-edge here. And you notice that in terms of the primitive closed even walks, the 2-4 cycles and the outside 6 cycle, the way you get from here to here is by simply substituting E equals F equals 1. So it's kind of very easy in terms of figuring out, what the new generating set is for the star contraction. In terms of GVDs, what we have so far is that the degree 2 case is easy. So as long as things are degree 2 before and after the star contraction, then it's going to be an if and only if. So those are kind of just, you have this path and you kind of start contracting it down to just something simple with just 2 or 3 edges. The other one, which was not as easy, is that if IG is GVD, and again, under some conditions about being square free, then the star contraction will also be GVD. And in the problem set, we put some open questions at the end. There's stories behind these open questions. I have other open questions. So if you're excited about graphs and trying to figure out some of these problems and just, taking a stab at some of these, then you can talk to me afterwards and I can tell you kind of some of these problems. Really, it's just, let's start the classification process, and any tools that we can create to help that classification will be helpful. I think I'm out of time, right? 10:20? Yeah, okay. Thank you.